could start.
Hi, I'm Jordy, and this is Yafir, and we're working on the AYAB project through the Making Fashion Accessible VIP. Our project mainly focuses on combining hardware and accessibility, and we're working with a Brother KH910 knitting machine and using an Arduino with it, with the AYAB system to try to modernize how it works. So overall, we're really looking at how we can take an older machine and make it easier to use and more accessible through technology. So for our project, we're working with the Brother KH910 knitting machine, but we're not focusing on the whole technical side. We're also looking at it from a fashion and accessibility perspective. For a lot of older knitting machines, they rely on old punch cards and manual systems, which can be limiting and harder for beginners or people with different needs to use. Through our blog research and hands-on work, we've been exploring how these barriers show up in real use, especially when it comes to learning and interacting with the machine. For example, users with muscle atrophy may struggle with the physical effort required to operate the carriage, handle different materials, or repeatedly perform manual inputs, which highlights the need for more accessible, digitally assisted systems. Our research goals were to understand how the machine works and identify any accessible challenges in the current workflow and explore how digital control through AYAB could improve the overall user experience. To address that, we're using the AYAB system, which replaces the original control system with an Arduino and a custom board, which allows the machine to be controlled through a computer. This lets the patterns be digitally created instead of manually, which can make the whole process more flexible and easier to understand. Along with installing and testing the hardware, we've also been documenting our process and challenges so that the future users can better understand both the technical setup and the user experience side of working with the machine. Our design and collaboration process involved working closely together to divide the tasks like soldering, research, and documentation while using resources like Discord and online guides to troubleshoot and improve our whole setup. This slide shows what it looks like when you create a pattern using the AYAB software and then send it to the knitting machine. On the left, you can see the stitch pattern being designed digitally, where each square represents how the needles are going to be selected. That pattern is sent from the computer through the Arduino and into the machine, which translates it into physical stitches. On the right, you can see the actual output from the machine, showing how the digital design becomes a real knitted pattern. Our main goals for this project were to first understand how the machine works, both mechanically and electronically. From there, we wanted to properly set up the Arduino and AYAB board to replace the original control system. We also focused on getting the firmware running and testing communication between the computer and the machine. And overall, one of our biggest goals was to make the setup easier to understand for future users, especially since a lot of documentation can be confusing. For our research, we looked into a few main sources. First, the AYAV manual site, which gives us a step-by-step instruction for installation, setup, and troubleshooting. We also use the AYAB website, which explains how the system works overall and what it's designed for. The GitHub repository was an important role for understanding the actual code and development side of the project. And finally, we used the YouTube videos and AYAB Discord, which were really helpful for seeing real examples, troubleshooting issues, and getting any help from the community. From this research, one of our main takeaways was that while AYB makes these machines more powerful, the setup process is still complex and not very beginner friendly. This reinforced our focus on improving documentation and making the system more accessible and easier to understand for future users.
So before diving into what we did, it helps to see what already exists in the world if someone wants machine control knitting today. There's basically three tiers. On the high end, you have modern electronic machines, Knitterit, Silver Reed with Designate, and then the industrial Shima Seiklet machines. These are turnkey. You can digitally input patterns, but they're expensive, anywhere from 4,000 to over $100,000, and they're closed ecosystems. You can't really hack them. In the middle, you have the legacy path using Designate software with the original KH930 or 940 mainboard. The problem is the cables are aging, the serial connection is flaky, and the software is from the Windows 95 era. The hardware itself is becoming almost impossible to find. And then on the DIY and open source end, there's AYAB. All yarns are beautiful. That's where we come in. It's an Arduino Plus, a custom shield that fully replaces the original mainboard, and the bill of materials is done somewhere between $40 and $80. It does require soldering and hardware literacy, which is part of what Jordy and I have been learning this semester. So our lane is really that bottom path, keeping these legacy machines alive with open, repairable infrastructure. This is where we're aiming. There are four pieces we want to land by the time this work is done. The first is the core technical goal, the AYB shield replacing the KH910's pattern logic. The Arduino and shields together substitute the original mainboard, and they translate digital pattern data into row by row needle selection across all 200 needles. That's the main event. The second is verified hardware before power on. This is something we've been deliberate about. Continuity test, visual inspection under magnification, reflowing any joints that look uneven. We're treating solder quality as a functional requirement, not something cosmetic. The documentation we follow is really explicit that most failures aren't software bugs, they're also soldering issues. The third piece is accessibility center documentation. The AYB workflow as it exists today assumes a lot. Visual acuity for reading schematics, fine motor control for soldering, certain kinds of technical literacy. We want to rewrite that workflow with clear visual, plain language, and framing that accounts for different visual and motor needs. The idea being that documentation itself can function as an accessibility tool. And the fourth is a maintenance partnership with with the machine maintenance group. The KH910 is a legacy machine. Needle selection sensors are 30 plus years old. So we can't just handle the electrical side and walk away. Electrical work has to pair with ongoing mechanical reliability. This is where we actually are. On the completed side, first we had our kickoff meeting where Jordy and I scoped the research direction. We framed the learning goals around how the KH910 actually works, what the major hardware failure modes are, and what accessibility considerations should guide the work. Second, literature and reference gathering. We worked primarily from Victoria Pollock's soldering guide, which is also open source and published under Creative Commons. It's written for the KH930 and 940, but the assembly workflows translated well as baseline. Third, we soldered the AYAB shield board itself. That meant getting the LED polarity right, red, yellow, green line with the silk screen, placing the 150 ohm and 10K resistors correctly, soldering the machine connectors with careful consideration checks, mounting the Arduino headers on the underside using the Arduino itself as alignment aid, installing chip sockets first before the ICs to prevent heat damage, maintaining and stabilizing the sensors ribbon cable. And fourth, we're currently in hardware verification, visual inspection under magnification, reflowing any uneven joints, continuity testing, and checking for shorts before we ever apply power. On the right side, what we haven't reached yet. We haven't connected the shield to the machine live. We haven't done a power test with a binary pattern, and we haven't observed actual row by row needle selection. The reason, honestly, is that legacy hardware is unforgiving. Cold joints cause signal dropouts, bridge pads short data lines, and the KH910's own sensors and carriage are 30 plus years old. We chose precision over speed because if we'd rushed to build and power it up wrong, we could have damaged components that are generally hard to replace. Quick walkthrough of how the semester mapped out. Weeks 1 through 3, study phase. We spent the time understanding how the machine actually mechanically works, how the electronic needle selection system functions, and reviewing all the AYB documentation. That's complete. Week 3 through 5, solder phase. This is where Jordy and I did the actual shield assembly, following the step-by-step order from the manual. Also complete. Mid-semester is which is where we are right now. Verification, continuity testing, visual inspection, reflowing joints. This is a step where we make sure everything is electronically sound before we ever connect to the machine. Late semester coming up, which is around now, the test phase. Live connection of the shield to the KH910 in our first pattern trial. We want to upload a minimal binary pattern and observe whether the needles select correctly row by row. And lastly, documentation. Writing up what we learned, synthesizing the accessibility findings, and producing something future research groups can build on. We're on track through verification and tests and document phases are ahead of us. Splitting this in two halves, what's immediate and what carries forward. On the left this semester, our next action is integrating the machine connectors onto the verified shield. That means double checking connector orientation before attachment, making sure everything sits firmly, and confirming that our trim pins or our underside leads don't interfere with the Arduino. Once that's done, we connect the shield to the KH910 itself and power the Arduino via USB. Then we launched the AYB web interface and upload a minimal binary test pattern, something simple so we can actually see if needle selection is working. And we log anything that goes wrong, skip needles, timing lag, desynchronization. If issues come up, we troubleshoot across three layers: hardware, firmware configuration, and any mechanical issue with the KH910 itself. On the right side, next semester, the things we've identified as valuable that we won't fit into this term: a full accessibility audit from AYB workflow and interface, rewriting documentation specifically framed for users with different motor and visual needs, deeper research into the intersection of mini machines, assistive practice, and feminist making, which ties into the broader literature on the erasure of women's labor in computing history. Building out a more formal troubleshooting protocol, basically decision tree across hardware, firmware, and mechanical layers. And continuing the partnership with the machine maintenance group on long-term availability of the KH910, since this is a one semester fix. And that's where we are. Happy to take any questions. Thank you.